Let's revise the whole of AQA capacitors. This video will go through the AQA specification, however it is applicable to all exam boards. Let's start off with the definition of capacitance. So capacitance is defined as simply the amount of charge stored per unit volt. This is governed by the equation that C, the capacitance, is equal to Q over V. I often like to think of it this way. If I have a capacitor over here, then we're going to be able to store some charge onto it. Now, this charge will end up depending on two things. Well, the charge that we can store will depend on the voltage. For instance, if we were to connect this to a much higher voltage power supply, we're going to be able to store more charge. And the constant of proportionality between them is known as the capacitance. So in this equation, capacitance is measured with the unit, which is known as the Farad, which is just given the symbol F. So what is the Farad? So 1 Farad is defined simply as, well, 1 coulomb per 1 volt. Sometimes in AQA you can get questions such as state what is meant by a capacitance of 100 millicoulombs, and the answer of this is simply, typically this is a 2 marker by the way, so you can say something like 100 millicoulombs of charge are stored per unit volt, and 1 mark will go for this, and then 1 mark will go for this statement. Now let's look at parallel plate capacitors. Here is a parallel plate capacitor. So what do you think its capacitance will depend on? Well, if the area of the capacitor, let's see if I can draw it a little bit more in 3D, was a little bit higher, then the amount of charge stored per unit volt is likely to be higher as well. So the capacitance should be directly proportional to the area. If we were to bring the capacitors closer together, the relative electric field between them should increase, meaning the capacitance should also increase. So therefore, it's going to be inversely proportional to the distance between the actual plates. Now, there's some constants of proportionality there. If we simply have E naught here, and E naught is just a constant, which is the permittivity of free space. And this here is just a constant of value 8.85 times 10 to the power of minus 12. The units for that are force m to the power of minus 1. Okay, now this equation is true for a vacuum. However, if there is a dielectric, and a dielectric simply means an insulator that's placed between the plates of the capacitor. So, what have I done here? Let's try again. So this here is a dielectric. Then its capacitance will change, and we're going to get an additional constant, which is E subscript R. Now this here is our relative permittivity. This here typically is a number or a decimal, and it's going to be greater than 1 because we can't have permittivity smaller than the permittivity of free space. Now, what is meant by a dielectric constant? A few years ago, there was a question on the AQA spec which asked what is meant by a dielectric constant of a certain number. For instance, here I've just given 5, and over 90% did not include that definition, didn't gain the mark. So let's answer this. Well, a dielectric constant of 5 or any other number that it could be is simply given by a ratio. The dielectric constant is the ratio of the permittivity of the medium divided by the permittivity of free space. Another point on the specification is about polar molecules in dielectrics in the presence of an electric field. Now, this is probably best understood with an example question. For instance, we can have a dielectric which is inserted between the plates of a parallel plate capacitor, and its capacitance changes. Explain how. Well, if we think about it, if we have a parallel plate capacitor, let's see if I can draw one. Let's use the digital ruler feature over here. Here's my capacitor. Well, if we were to insert a dielectric between the plates, let's say that this here is our dielectric with some polar molecules. Okay, so the first thing to note is that there's going to be some electric field between the plates. Let's say that this is a positive plate and this here is a negative plate. There's going to be a field from positive to negative just due to the parallel plates of the capacitor. The first thing to note is that this dielectric will consist of polar molecules. Now, what does a polar molecule actually mean? Let's draw this not up to scale, but imagine that we have a molecule like this. This molecule will end up aligning, so maybe it was a different angle initially, in a way such that positive and negative are going to attract. So this end here will be negative and this end here will be positive. Let's draw this with red maybe just to make sure it's really visible. This is the negative end and this here is the positive end. And let's draw a few of these, negative and positive. After the molecules align, we can write that this produces its own electric field in the opposite direction. How does that work? Well, electric field lines go from positive to negative. You can kind of think of this as a little vector going this way, a little vector going this way, a little vector going this way, a little vector going this way. This diagram is not drawn up to scale, but the overall electric field between the plates is going to be reducing. Well, remember, if the electric field between the plates reduces, well, E is equal to V over D, which is voltage between distance. The distance is unchanged. And if the electric field goes down, then the PD between the plates must also go down. Okay, if the charge is to remain the same, remember C is equal to Q over V. So charge is constant, but the potential difference decreases, and this means that the capacitance must increase. Next, let's have a look at the energy stored by a capacitor. First, we need to look at the interpretation of the area underneath a graph of charge against potential difference. So this area over here is actually the energy stored by the capacitor. And it's worth noting down that the area underneath a charge against voltage graph is the energy. So in this case, this here would be just the area of a triangle. So the energy will be equal to a half base times height. Let's write this a little bit better. And I can write the formula here that energy is a half QV. Now there's a few alternative formulas given in the formula booklet, but also quite easily derived. Remember, Q is equal to C times V. Plugging this in here, we also get that the energy stored in a capacitor is equal to a half CV times V, which is going to give me CV squared. And we can also say that because V is equal to Q over C, we can sub that into here, and then we're going to get a half Q squared over C, which is yet another formula for the energy. Let's have a look at the graphical representation of charging and discharging of capacitors. We're going to start off with capacitors that are actually charging. So we can see that the charge on the unbalanced charge on the capacitor will end up increasing with time until it tailors off to some value. The same thing is going to happen to the potential difference across the capacitor. Please note that these are just rough sketches. Now, what's going to happen to the current and why is it actually decreasing? In order to really answer this, well, let's explore this with a little circuit. Imagine that I've got some power supply. Let's say that it has an EMF V0, and this thing here is just connected to a little resistor, and let's also connect this to a capacitor. Let's say that the capacitor's voltage is initially, well, it's V, and let's say that the voltage across the resistor is VR. Now, at the moment when we switch on the power supply, or should we just add a little switch over here? So imagine that suddenly we just close the switch. As soon as we close the actual switch, the capacitor, at the moment this happens, initially has a voltage of 0. What's going to happen to it over time? Well, it will end up increasing. By Kirchhoff's second law, that the sum of the PDs is equal to the sum of the EMFs, the voltage across the resistor will end up decreasing. This is actually an exponential decrease, and the expression for the voltage across the resistor is that VR is going to be equal to the initial voltage, which has to be the EMF, e to the minus T over CR. Let me just move this label over here like so. Find that a good way to visualize what is actually happening is to just think of some numbers. Now imagine that initially V0 is equal to 10 volts. Well, if that's the case, if the voltage across the capacitor is initially 0 and it ends up increasing, the initial voltage across the resistor has to be equal to 10 volts. Okay, well, let's say that the voltage across the capacitor increases to 1. This thing here will end up decreasing to 9. They have to keep adding up to 10 volts. Let's say that this one here increases to 2. This one here has to decrease to 8 volts, and so on and so forth. Keep adding up until they reach 10 volts. Now, after some time, the voltage across the capacitor will end up being 10 volts, and the voltage across the resistor will end up being 0 volts. If there is no voltage across here, there can't be any current. And we can see that the current in the circuit is steadily decreasing, and this is expressed in this graph over here, which is for the current in this circuit. Back to this circuit over here, we can see also that by Kirchhoff's second law that V0 has to be equal to VR plus the voltage across the capacitor, which in this case is just V. Okay, well, this means that the voltage across the capacitor V has to be equal to V naught take away VR. But hang on a minute, we've said that VR is equal to V naught e to the minus t over CR, and this right here means that V is going to be equal to V naught take away V naught e to the minus t over CR, and we could just factorize a factor of V naught, and we get V is equal to V naught 1 minus e to the minus t over CR. And this is the equation for a charging capacitor. Because Q is equal to CV and V is equal to Q over C, the same equation can also be applied for the charge across a charging capacitor, and those two equations right over here are the equations for charging of a capacitor. So how does a discharge of capacitor through a resistor actually work? Well, we're talking about this type of circuit where we don't have a separate power supply. Maybe we had before and we've blocked that part of the circuit, but now we just have a charged up capacitor that is discharging through a resistor. So the capacitor will initially have a lot of unbalanced charges, and then if the circuit, let's say it had a switch, and then we flip that switch and then we close the circuit, the charges are going to start traveling across the actual circuit. Initially they're going to be attracted by quite a lot of unbalanced positive charges, but then every time a negative charge arrives here, it will balance out one, and the overall potential difference will decrease exponentially with time. If the potential difference decreases with time, in this case the charge will also decrease with time, and the current will also decrease with time. And the same exponential equation can be applied in this case. When a capacitor is discharging, the voltage across the capacitor is equal to the initial voltage, and then we have this factor of minus t over CR. It's a negative exponential. The same equation can be applied for the current in this discharging circuit and for the charge in this discharging circuit across here as well. And these are the discharging equations for a capacitor. Sometimes they're a little bit tricky, and what I would advise you to do is to always look what is actually happening in a question. If a capacitor is charging, we have to use those equations. If a capacitor is discharging, we have to use those equations. And now let's talk about one of the most important concepts in capacitors, and this is the time constant. Now let's imagine that we have a little circuit, and once again we have a capacitor which is actually discharging. So maybe you had a switch initially, and then the capacitor discharges through a resistor. So after we close the switch, the discharge time on the capacitor will depend on a couple of things. So if the resistance is really high, then the discharge time is going to be a lot smaller because the current is going to be smaller. It will also depend on the capacitance, how much charge per unit volt this capacitor here will be able to store. Okay, so we can define a quantity which is the time constant that is equal to the multiple of the capacitance and the resistance. Now, just as a little side note, really interesting actually, the units of this quantity are very, very interesting. So if I was to multiply capacitance by resistance, well, capacitance, because Q is equal to C over V, this would mean that capacitance is just equal to Q over V. So I can just kind of plug this into here. And what I get is Q over V times R. Now, remember though, from first year, charge is equal to current multiplied by time, and voltage is equal to current multiplied by resistance. So just considering these units, we can see that if we were to multiply capacitance with resistance, we're going to get units of time. So this here is a time. What time are we actually talking about? Well, the equation which governs the discharge of this capacitor and the voltage across it is given by V is equal to V naught e to the minus T over CR. So, well, let's say that T is equal to CR, then we're going to get that V is equal to V naught e to the minus CR over CR. But hang on a minute, have a look at this. Those CRs are going to cancel, and then what we're left with is that V is equal to V naught e to the negative 1. An alternative way of writing this, that this is equal to V naught times up to two significant figures, is around 0.37. And this here is the definition of the time constant. It is the time after which the PD during discharge drops to 1 over E of its initial value. And let's have a look at the halving time of a capacitor. Once again, we have our typical circuit with a little capacitor that's discharging for a resistor. Maybe we had a little switch over here that we've closed already. So what's going to happen? At what time will the PD across the capacitor actually halve? Let's assume that we start with some initial voltage across the capacitor, V naught. Well, the equation is that V is equal to V naught e to the minus T over CR. So at the halving time, let's say T is equal to T of a half. So this is actually given typically in AQA a capital letter. So let's write it like this. We can say that the voltage is equal to V naught over 2. So this means that in our equation, V is going to be just V naught over 2 when T is equal to the halving time, and then we get V naught e to the minus T half over CR. The two V naughts are just going to cancel out, and then what we're going to get is a half is equal to E minus halving time over CR. Now let's take the natural log of both sides so that we get rid of the exponential. So it's going to give me minus T half over CR. This is just a subscript for the halving time, by the way. Now, due to the properties of logarithms, the negative sign, if we multiply both sides by -1, will actually flip the fraction inside of the logarithm. So multiplying both sides by -1, we get ln of 2 is equal to the halving time over CR. Okay, finally we get our expression that the halving time of a capacitor is equal to ln of 2 multiplied by CR. So N1 of 2, it has a mathematical value, and the way it's typically given is 0.69, multiply this by CR, and this here is the expression for the halving, or the time for the voltage across the capacitor to halve, and the same equation once again can be applied for the charge across the capacitor to halve and for the current in the circuit to decrease by that factor. We can also determine the time constant from graphical data. For instance, we might be given a graph of voltage against time. In order to work it out, we need to remember that after time is equal to the time constant, the voltage and the charge and the current decrease to 37% of their initial value. So the first thing is to look at the initial value. In this case, this here is 6 volts. And then what I'm going to do is just multiply this by 1 over E, which is just E to the minus 1, which is 37%, roughly 1 over E. Okay, so this here is the initial voltage divided by E. So that's also roughly equal to 6 times 0.37, which is about equal to 2.2 volts. So whenever the capacitor reaches 2.2 volts, which is right over here, and this happens at 50 seconds. So for this particular graph, the time constant is equal to 50 seconds. And then if we were given the resistance, for instance, we could even work out the capacitance from this graph. This type of question can also appear for a different graph. This could be Q or this could be I, but it will be exactly the same way. Find the initial value, divide that by the constant E, and or find 37% of it, and then this here, find the corresponding time. This here is your time constant. Okay, folks, now this was all the theory from the AQA specification, and it's really important to apply these to problems. And it's really important to apply this to problems. This is precisely why you should have a look at this video right over here. Enjoy and have a look at a really difficult problem.